All right, there's one more form under a reducible to homogeneous differential equation. And that form is basically of the type dy by dx is equal to a linear expression, let's say ax plus by plus c over, let's say px plus qy plus r. Okay. In such forms, you would realize that just because of the presence of a 0-degree term both on the numerator and in the denominator, we are not able to directly apply our methodology of converting or solving a homogeneous differential equation in this case. So how do we approach these kind of problems? Let me illustrate this through a simple example. All right, so let's have a look at this example. So here we can see that we have been given a differential equation of the very same type as I was talking about a little while ago. Dy by dx is equal to a linear expression, x plus 2y plus 3 over 2x plus 3y plus 4. Okay. In such kind of problems, we use the idea of shifting of origin. So what we will do that here is we'll take this variable x to be a new variable, let's say capital X plus h, and small y as a new variable capital Y plus k. Now you would think, what is this h and k? This h and k are to be found out in such a way that this entire differential equation gets converted to a homogeneous differential equation. So first, let me tell you, by shifting of origin, the expression for dy by dx, that is d small y by d small x, still remains d capital Y by d capital X. Okay, there is no change. Remember, the slope at any point, if it is shifted in space, doesn't change in this particular case. So what we are going to do is we are going to change the entire differential equation in terms of the new variable. So small dy by small dx will be changed with d capital Y, d capital X, and small x will be written as capital X plus h 2 times capital Y plus k plus 3 over 2 capital X plus h 3 capital Y plus k plus 4. In other words, it gives you capital X plus 2 capital Y plus small h plus 2k plus 3 over 2 capital X 3 capital Y 2 small h 3k plus 4. Now, we can all make a guess over here that if you want it to be a homogeneous differential equation, these two terms must not exist. That means these two terms must be 0. Correct? Indirectly, our choices of h and k would be governed by the solution of these two simultaneous equations. Okay, we can also solve the simultaneous equation. When we do that, we'll get the value of h in this case as 1 and k as -2. Having known these values of h and k, we can go back to this differential equation. Let me call this as equation 1, and just remove the constant terms both in the numerator and denominator. That is, we will only be left with x plus 2y over 2x plus 3y on our right hand side. Now this is a perfect ground for us to apply our substitution. Capital Y is V capital X. Okay, the normal procedure that we follow for solving a homogeneous differential equation. That means dy by dx is nothing but v plus x dv by dx. Okay, so converting everything here, v plus x dv by dx is equal to x plus 2 vx by 2x plus 3 vx. Okay, so this converts further into v plus x dv by dx is equal to 1 plus 2v over 2 plus 3v. Okay, now after that, the procedure is pretty much simple and evident to all of you. We take the v term on the other side and try to give it a form of a variable separable. So which is as follows. So as you can see, if you take the LCM here, 2v will get cancelled, giving you the expression of 1 minus 3v square over 2 plus 3v. Okay. Now, separating the variables out, it will become 2 plus 3v over 1 minus 3v square dv is equal to dx by x. Now, let's integrate both the sides. On the left hand side, I will try using partial fractions to solve this. So let me first take this term up and break this as 2 plus 3v by root 3v plus 1 into root 3v minus 1. Okay, essentially I have used the formula of a square minus b square over here, splitting it up as a minus b times a plus b. Okay, now we know the rule of partial fractions, so we try to split the denominator factors in this form, correct, and try to get the value of a and b through a smart substitution or through the coefficient matching on both the left and the right hand side of the equation. Please note, this is not an equation that you are solving. This is a term which is both the same terms on both the sides of the equation. So it is like a identity. Okay. So for any value of v on both the sides, this identity will remain true. This identity will hold true. So let us find the value of a and b in this case. So you can also try it from your end. So the value of a that you will get from here is going to be root 3 minus 2, and the value of b that you are going to get from here, in fact, root 3 minus 2 over 2, and the value of b that you are going to get is root 3 plus 2 over 2. So using this partial fractions expression over here, I will get integral of 2 plus root 3 over 2 root 3v minus 1 minus 2 minus root 3 by 2 root 3v plus 1 dv is equal to integral of negative dx by x, right? Now, through our understanding of indefinite integrals, we are well versed with the integral of these two expressions, and that would be nothing but 2 plus root 3 by 2 ln of root 3v minus 1 divided by root 3, okay, minus 2 minus root 3 by 2 ln root 3v plus 1. Okay, and on the left hand side we'll end up getting minus ln x plus a constant of integration. Okay, now once we have achieved this stage, all we need to do is put our v back as capital Y by capital X and put our capital X and capital Y in terms of small x and small y as per this relation that we had started the problem with. So we had started our problem with the fact that our small x and small y are related to capital X and capital Y by this relation. That means capital X is small x minus h. Now remember, h was 1, so it will be x minus 1. And capital Y will be small y minus k, small y minus k, which is small y plus 2. Okay, now using these values back in our answer over here, okay, I think there's a lack of space over here, but all you need to do is you need to replace your, I'll just write it down, you need to replace in this expression final answer, you need to replace your capital V with capital Y by X, which is nothing but small y plus 2, as we had discussed over here, small y plus 2 by small x minus 1, by small x minus 1. So once you make this replacement in your answer over here, so please make this replacement in your answer over here, you get your final result, right? Now, the bottom line behind this problem was to make you understand that whenever you have problems of this nature, where you have a linear term divided by another linear term, okay, where because of this constant, you cannot directly use your fundamentals or concepts of homogeneous differential equation. You can take the help of shifting of origin concept to achieve that. Okay, many times substitution also works, but there x plus 2y should be linked to this term. For example, if there was x2x plus 4y term over here, then it would have been a case of reducible to variable separable form, because in that case you would use x plus 2y as your v and proceed with the problem to directly convert it to a variable separable form. But in that case, but in situations where that is not possible, we need to rely on the concept of shifting of origin and making these constant terms appearing here as 0, thereby making it a homogeneous differential equation of this nature, and then proceeding it in our normal way. Now next we are going to move to another important type of differential equation, which we call as the linear differential equation. This is going to be one of the most commonly asked question both in your school exams and competitive exams. What are linear differential equations first of all? In plain and simple words, a differential equation is said to be linear if an unknown variable and the derivative occur only in the first degree. That means your dependent variable y and all the derivatives or differential coefficients, they occur only in the first degree. A typical structure of a linear differential equation is of this type. Let's say ANX. Now when I say ANX, means it's a function of x. Nth derivative of y with respect to x plus an minus 1x y by dxn minus 1 can go all the way till a naught x y is equal to f of x. Here your ai x and f of x are functions of x or constants, are functions of x or constants. Please note, I have written this linear differential equation treating y as my dependent variable and x as my independent variable. You could also write a differential equation in the other form as well, where you can have something like this: any dnx yn an minus y dn minus 1x dyn minus 1 all the way till a1y dx by dy plus a naught yx is equal to fy. Right here your aiy and f of x are functions, f of y are functions of y or constants. In fact, constants are functions of any variable, are functions of x or constants. Okay, so this is a linear differential equation structure where here my y is a dependent variable, x is independent, and in this case my x is a dependent variable and y is an independent variable. Okay, as you can see from the definition of a linear differential equation, what did I tell you? I told you that your y term and all the differential coefficient must occur in the power of 1. So as you can see, they all have, these all differential coefficients have power of 1. Okay, I'm repeating the definition once again. A linear differential equation is one in which where the unknown variable, that is y in the first case and x in the second, and its derivative occur only in the first degree. Now, our subject area for JEE Main and JEE Advanced is to deal with linear differential equation of first order only. So we'll not talk about any higher order linear differential equation. So we'll restrict our conversation and discussion only to first order linear differential equation. Only to first order linear differential equation. Under the first order linear differential equation, you may come across these two types of linear differential equation. One is of this form. Remember here, y here is the independent variable. Y is your dependent variable, x is independent. And px and qx are functions of x or constants, are functions of x or constants. So this is the first type of differential equation under first order linear differential equation that we are going to come across. The second type is where your x is the dependent variable, something of this nature, dx by dy plus py x is equal to qy. Okay, here your x is a dependent variable and your py and qy are either functions of y or constants or constants. So how do we solve this first order linear differential equation? So let me begin with the very first type, okay, which was dy by dx plus p, which is a function of x, y is equal to q. Okay, so here p and q are functions of x or constants. Okay, actually I have dropped the x term. Normally in the previous example I had written p as a function of x and q as a function of x, but I've dropped this x just in order to save my time and effort and to avoid any type of confusion. Okay, now in order to solve this, what we do is we multiply both the sides of this differential equation by a term which we call as the integrating factor. So we multiply this differential equation both the sides, okay, I'm just writing it like this, both the sides by a term which we call as the integrating factor, and that is nothing but in e to the power integral of p dx. Yes, the very same p that we have over here. Okay, and this side also we'll do the same multiplication, e to the power of integral p dx. Okay, please note this term e to the power integral p dx, when you are writing it, please do not put any constant of integration while you are integrating p with respect to x on the exponent of e. Okay, this term here, let me write it here, where this term is called as the integrating factor. This term is called the integrating factor. In short form, I'll refer this as IF. I'll refer this as IF throughout our discussion of linear differential equation. So step number one, as I already told, multiply both sides with the integrating factor. What is the integrating factor here? E to the power integral p dx. Again, a word of caution, while you're doing integral p dx, do not put any constant of integration there. Okay. What is the benefit of doing this? If you expand this term, you'll see that you end up seeing this expression, e to the power integral p dx into dy by dx plus y into e to the power integral p dx into p is equal to q e to the power integral p dx. Now you must be wondering what great has happened by doing this. If you see this term very, very carefully, you'd realize that this term is nothing but it's the derivative of y into e to the power p dx. So if you apply product rule on this, you would start realizing that this actually gives you this expression, right? Very obvious. If you treat your first term as it is, differentiate y with respect to x, it becomes dy by dx, correct? Plus treat y as such, the derivative of this term e to the power something is e to the power something into derivative of an integral is nothing but p itself. That is what is being obtained here in the curly bracketed terms. Okay, so I am going to just remove this and continue with our next step over here. So here you have been successfully able to convert this as an exact differential. So this is a differential of an exact expression like this. Okay. Now this is the kind of a variable separable where you have two types of variable with you. One variable is this variable itself. This entire thing can be called as one variable itself. And other variable is basically a function of x over here. Please note that this completely is a function of x. So this multiplied with dx. So what I have done is the denominator dx, I have just taken it to the right hand side. Okay. So ultimately at this step, I call this to be variable separable form. So this is a variable separable form. So you can use the variable separable methodology, or you can directly integrate both sides over here because it has been already been in the exact differential form. So here the derivative of d something is the same something. So y e to the power integral p dx. Again, I am repeating, while you are doing e to the power integral p dx, do not put any constant of integration. Okay. And on the right hand side, you'll get q times, q again is a function of x or could be constant also. You end up getting this expression. Okay, please integrate this again with respect to x and just put a constant of integration at the end, and you are done with the solution of this linear differential equation. Right? Now guys, I'm not completing this problem over here. I'm stopping it right now because I don't know what is q. So everything will depend upon what is your q and p in the question. But this is the general structure of the solution. So please remember this. This is going to be used at so many places. You don't have to do the same procedure as we followed to derive this formula for solving all the problems. Once you know it's a linear differential equation, once you know it's an LDE, you can directly jump to this formula. Now a natural question will arise in your mind, what about the other situation? What about the second situation where your dependent variable was x? Very simple. All you need to do is do a role change. So in the dependent variable x linear differential equation, let's say, let me write it down first. This is the form. Here p and q are functions of y. Remember, p and q are functions of y or constants. Okay, constants can be treated as functions of any variable, so it doesn't matter. In this case, you will follow the same here. Whatever solution that you obtain, is just that there will now be a role change. Y will be replaced by x. E to the power, that is your integrating factor, will now become e to the power p dy. And on the right hand side, you'll have q times into the integrating factor e to the power p dy, whole derivative integral with respect to y, and just put a constant of integration towards the end. Okay, and that's how you can solve your LDE of first order, linear differential equation of first order. Please remember this result. So depending upon the question, whichever form is given to you, you can directly start with your structure of the solution over here. Let me take some examples to illustrate this. So in this problem, we can see that you can write this linear differential equation as dy by dx plus 1 over x squared times y is equal to 1 over x squared. Okay. Now try to compare this with the type 1 linear differential equation which we had discussed a little while ago. So here you can see that the role of p is being played by 1 over x square and the role of q is being played by 1 over x square also. So both p and q are the same functions over here, which is 1 over x square. Okay. Now what is my integrating factor over here? Integrating factor is e to the power integral p dx, which is nothing but e to the power integral of 1 by x square dx, which is nothing but e to the power minus 1 by x. Okay, don't have to put any constant of integration while you are writing IF. Okay, so directly using the structure of our answer that we had discussed a little while ago, we can say y into integrating factor, which is e to the power minus 1 by x, is equal to integral of q times, which is again 1 by x square into e to the power minus 1 by x dx. Correct? Now here in the second integral, which is on your right hand side, you just have to take minus 1 by x as your t, right? So 1 by x square dx becomes your dt. So this becomes e to the power t dt type of integral. correct? Which is nothing but e to the power t plus a c. So your final result will now become y times e to the power minus 1 by x equal to e to the power t. T is nothing but minus 1 by x plus c. So that will become minus 1 by x plus a c. Okay. If you want, you can further refine this answer by dividing throughout with e to the power minus 1 by x. So y will become 1 plus c e to the power 1 by x. So this becomes your answer. All right, so let us have a look at another problem which is based on linear differential equation. I would request you all to pause this video at this point of time and try it out yourself. All right, so assuming that you all have given it an honest try, so let's discuss it now. So this expression, first of all, let me take the dx by dy term on the other side. It will become dy by dx is equal to e to the power negative 2 under root x by root x minus y under root x. Okay. Let's bring this term to the left hand side. It becomes dy by dx plus y under root x e to the power negative 2 root x by root x. Now, right now, this problem has been converted to a linear differential equation of the very first type that we discussed. So please compare this with dy by dx plus py equal to q. So by comparison, we can clearly make out that p is 1 by root x and q is e to the power minus 2 root x by root x. Okay. So what is the integrating factor now? So integrating factor will be nothing but e to the power integral of 1 by root x dx. Okay. Which is nothing but e to the power of 2 root x. Is that fine? So according to our solution structure for linear differential equation, let us write down y into integrating factor, which is e to the power of 2 root x equal to integral of q. This is my q times integrating factor, which is again e to the power 2 root x dx. Right? Now you can see that these two terms will take care of themselves and it will just become y e to the power 2 root x is equal to integral of 1 by root x dx, which is nothing but 2 root x plus c. So your final result will now become y e to the power 2 root x is equal to 2 root x plus c. That is the solution for this differential equation. Now let's give a try to this problem. So here again we have been given a differential equation cos square x times dy by dx minus y tan 2x is equal to cos to the power 4x. But apart from that, we have been given some additional condition that mod x is less than pi by 4 and y of pi by 6 is 3 root 3 by 8. I would request you all to pause this video at this point of time and try it yourself. All right, so assuming that all of you have given it an honest try, let us try to solve this. So first of all, let me try to convert this to the standard linear differential equation form. So I will divide throughout with cos squared term. So that is going to give me dy by dx minus secant square x tan 2x is equal to cos square, in fact there is a y term also, in equal to cos square x. Okay. Now comparing this, so compare this with dy by dx plus py is equal to q form. It is very clear that p is nothing but negative secant square x tan 2x and q is your cos square x. So if p is this, let us see what is our integrating factor. Integrating factor is nothing but e to the power integral of p dx. So this is our p dx. Correct? Let us convert our tan 2x in terms of tan x. So this is going to give you integral of, we can observe this minus sign by just switching the position of the denominator terms. So we can say tan square x minus 1 into secant square x. Okay. So in this integral, you can assume your tan x to be t. So let your tan x to be t. So secant square x dx will become dt. So this will become e to the power integral 2t by t square minus 1 dt, which is nothing but e to the power ln of t square minus 1 mod, which is nothing but mod of t square minus 1. Okay. Now this is a very important step, because here we need to decide whether the answer will be actually t square minus 1 or 1 minus t square. Now let us try to recall the condition given to us in the problem. Here I am dealing with such mods, here we are dealing with such x whose mod is less than pi by 4. So if mod of x is less than pi by 4, we can say that tan x will be less than, or you can say mod of tan x will lie between minus 1 and 1. Correct? That means tan square x will be less than 1, which means tan square x minus 1 would be negative. Right? If that is the case, we need to write this integrating factor as 1 minus tan square x, because we all know mod has to give you a positive answer. Right? So mod tan square x minus 1 under the impact that your mod of x is less than pi by 4 can be written as 1 minus tan square x. Okay, so this becomes our integrating factor. Now, once we know our integrating factor, we can directly apply it to the solution structure. Y into integrating factor, which is 1 minus tan square x, equal to q times integral of q times integrating factor, which is cos square times 1 minus tan square x. Okay, this is pretty obvious, because when you expand it, you are going to see cos square x minus sin square x, right? And we all know it's actually cos of 2x. So you are integrating cos of 2x. That's nothing but sin 2x by 2. Okay, and of course a c has to be put at the end. So ultimately, this is the solution, the general solution that we see for this linear differential equation. Now remember, we have been given additional conditions to get the value of c. It has been provided to us that y pi by 6 is 3 root 3 by 8. Let us use that to get the value of c. So let me put y as 3 root 3 by 8, and let me put x as pi by 6. Okay, so when we do that, so put this in this equation. So we end up getting 3 root 3 over 8, 1 minus tan square x, 1 minus tan square pi by 6 is 1 by 3, is equal to sine of pi by 3 half of it, which is half root 3 by 2 plus a c. Correct? Let me expand this further. 3 root 3 by 8 into 2 by 3 is equal to root 3 by 4 plus c. I think this 3 and this 3 and this 4 and this will cancel each other out, giving you c value as ultimately 0, because this entire thing and this entire thing becomes the same. So our final particular solution for this differential equation will now become y 1 minus tan square x is equal to half of sine 2x. So this becomes your particular solution. Remember, the earlier case, c has been now substituted finally. So the general solution was with the c in place, and if you replace the value of c with a value of 0 in this case, it becomes your particular solution. So this is the particular solution. Now again, let us look at this problem. Please pause the video and try it out yourself. So hope you have given it an honest try. Now let us discuss this. In this case, if you see, this problem is more related to the differential equation, linear differential equation of the second type that we had discussed early on. So what we'll do is, we'll first reciprocate this entire expression. So left hand side, dy by dx, reciprocate it as dx by dy. Right hand side will become 2y ln y plus y minus x by y. Okay. So when you expand this, it becomes dx by dy is equal to 2 ln y plus 1 minus x over y. Let's take this term to the left hand side. So dx by dy plus x by y is equal to 2 ln y plus 1. Now try to compare this. Now try to compare this with the linear differential equation dx by dy plus px is equal to q, where p and q here are functions of y. P and q are functions of y. So I would like you all to have a clear-cut demarcation, distinction, and identification for both the types of differential equation. So P here is 1 by y, Q here is 2 ln y plus 1. Right? So integrating factor is nothing but e to the power 1 by y dy, which is nothing but e to the power ln y, and that's y itself. Don't put any constant of integration. I'm reminding you all once again. So your final result would be x into integrating factor equal to q times, q is 2 ln y plus 1 into y dy. All right. So let us try to address this here. Now in this case, you would realize that this term over here is an exact differential. How? Let me show you. Let me take this term slightly separately. So if you see this term 2y ln y plus y, okay, this term has been obtained by finding the derivative of y square ln y. Okay, so you are trying to integrate this term actually, right? So if you see this term, this entire term is an exact differential of y square ln y, right? So when you do that, it becomes xy is equal to integral of differential of y square ln y, which is quite simple. It becomes y square ln y plus c. That's it. We are done with the problem. Now these type of identifications can be done once we are through with the exact differentials, which we are going to deal with in next form. All right, so let's have a look at another problem. Again, request you all to pause this video and try it on yourself. Okay, so let's discuss this now. Now, in the present form, this particular differential equation looks, very confusing. It is not in the right structure for us to identify whether it's a linear differential equation or not. So what we'll do is we have to be slightly vigilant. We see a term basically having functions of y. Okay, functions of y are occurring 1 plus y square and e to the power tan inverse y format. So what I'll do here is I'll try to convert this problem as the second type of linear differential equation. That is your dx by dy plus px equal to q form. Okay, how do I do that? Let's figure that out. So this expression, let me rewrite this. Let me multiply throughout with dx by dy. So let me multiply this entire expression, multiply this with dx by dy. Okay, so when you do that, it becomes 1 plus y square dx by dy plus x minus e tan inverse y equal to 0. Correct? So dx by dy plus x by 1 plus y square is equal to e to the power tan inverse y by 1 plus y square. So what I did was I just took e to the power tan inverse y to the right hand side, and then I divided throughout with 1 plus y square. Okay. Now at this stage, please compare it with dx by dy plus px equal to q form, where p and q are functions of y, where p and q are functions of y or constants. So you can see clearly that the role of p is now being played by 1 plus y square. The role of q is now being played by e to the power tan inverse y by 1 plus y square. Correct? Let us find out the integrating factor. Integrating factor would be e to the power integral of this term, which is e to the power tan inverse y. Don't put any constant of integration. I'm reminding you here again. So finally, putting it into the structure of the solution that we had derived, y e to the power tan inverse y is equal to integral of q times, that is e tan inverse y, by 1 plus y square into e to the power tan inverse y dy, right? Okay. So if you take e to the power, these two terms together, it will become 2 tan inverse y by 1 plus y square dy. I'm sure we can easily integrate our right hand side of the expression. We can just take e to the power 2 tan inverse y to be t. Okay. So differentiating both sides with respect to y, it becomes e to the power 2 tan inverse y into 2 by 1 plus y square dy is equal to dt. Correct? So this becomes this term excluding 2, or you can just bring this 2 down over here. Bring this 2 down over here. This term is already present in our given expression. Correct? So I can write this as dt by 2, whose integration is going to be just half of t. Okay, plus a constant of integration. Let me put the values again back. So finally, recording the solution. So your answer is going to be x e to the power tan inverse y is equal to half t. T is e to the power 2 tan inverse y plus c. Okay, so this becomes your final answer for this differential equation. So this becomes your final answer for this differential equation. Now, there are many problems which are not directly linear differential equations, but they are reducible to linear differential equations by making use of certain substitutions. So now we are going to look at some examples which are of the type reducible to linear differential equation. Reducible to linear differential equation. Okay, I'll try to explain this through a simple example. Let us take this question. Dy by dx is equal to e to the power x minus y times e to the power x minus e to the power y. Okay. Now, in this particular form, we can see that it is not variable separable for sure, right? Neither it belongs to reducible to variable separable nor homogeneous. Okay, so whenever you have been provided any differential equation, this is the trend which we follow. We start from variable separable and try to see whether variable separable form can be seen in that given differential equation. If not, is it reducible to variable separable? If not, it is homogeneous. If not, it is reducible to homogeneous. If not, then we try out our linear differential equation concept. So if you look at this present question, it doesn't satisfy anything which we have discussed so far. So what we'll do here is we'll multiply e to the power y throughout. So let's do that. So e to the power y dy by dx is going to give you e to the power x. Okay. This term is going to be e to the power x minus e to the power y. Let's expand this. Let's expand the right hand side at least. So e to the power y dy by dx is going to be e to the power 2x minus e to the power x e to the power y. Okay. Let me bring this term to the right hand side. So it becomes e to the power y dy by dx plus e to the power x e to the power y is equal to e to the power 2x. Now what I'm going to do next is I'm going to substitute e to the power y as v. Again, note v is another variable that we are substituting in place of e to the power y. It is not a constant. So differentiate both sides now with respect to x. So you'll get e to the power y dy by dx is nothing but dv by dx. Put it back over here. It becomes dv by dx plus v into e to the power x is equal to e to the power 2x. Now, if you see this differential equation very carefully, you would realize that there is just one small change. I'm not mentioning any y over here. I'm just mentioning in terms of v. Okay. So this is a differential equation where your v is the dependent variable. Okay. So you can see this as something of this type: dv by dx plus pv is equal to q. Okay. It's just a change of the name of the variable, nothing else. P is here e to the power x, q here is e to the power 2x, and both are functions of x. So we can use the same structure of the solution of the linear differential equation over here as well. So I would write v into integrating factor. Okay, let me first find out the integrating factor. Integrating factor here would be nothing but integration of e to the power x. Correct? Which is nothing but e to the power x. Okay, so v into e to the power x, that is going to be your integrating factor, is equal to integration of e to the power 2x into e to the power x dx. Okay, now the problem is, how do we integrate this? That's easy. You take e to the power x as t, so let e to the power x be t. That means e to the power x dx is your dt. Correct? So we can break this structure as e to the power x, e to the power x into e to the power x dx. And this is going to behave as your dt. So t e to the power t dt is what you are going to get on this side. Okay. Now this is a clear-cut case of integration by parts. Okay. And I'm going to apply my DI method to do that, because that's quite, efficient in these type of problems. So DI method is where you, or we call it as crisscross or tic-tac-toe method, where you write the function u under d and function v under I. So t is your u here and e to the power t is your v over here. So keep on differentiating under d. So this will become 1 and this will become 0. Keep on integrating under I. So this will be e to the power t, this will be e to the power t. Now what we do is we assign alternating plus minus plus sign and just do a cross multiplication like this. Correct? So your answer will be plus t e to the power t, which is t e to the power t, minus 1 e to the power t, which is minus e to the power t. Okay, so this will become t e to the power t minus e to the power t plus a c. Is that fine? Is that clear? Let's put back our v and we'll put back our t as well. So our final answer for this will now become v is nothing but, let me write it over here. So you had v e to the power x is equal to t e to the power t minus e to the power t plus c. So v is nothing but e to the power y itself. So e to the power y into e to the power x, and t is e to the power x. So e to the power x into e to the power x minus e to the power x plus a c. Okay, so this becomes the solution to this differential equation. Now the main agenda behind taking up this problem was to illustrate the fact that it is reducible to linear differential. It was not linear differential in the first place, right? To begin with, ab initio, it was not linear differential equation. But by making a substitution over here, that is e to the power y as v, I converted it to a linear differential equation and then applied my normal process. Now, under reducible to linear differential equation, there is one more very important form which we call as the Bernoulli's equation. Basically, it's a special type. Let me write it down. It's a special type under reducible to linear differential equation. Under reducible to LDE. How does this Bernoulli differential equation look like? It looks like something dy by dx plus py is equal to qy to the power n. Okay, here p and q are functions of x or constants, are functions of x or constants. Okay, but here there is an unwanted term y to the power n. Okay, so how do we deal with such situations? Very simple. We divide both sides by y to the power n. See, if this n was 0, it would have been a linear differential equation that we had discussed early on, right? But because this, let's say if this n is not 0, then unnecessarily this term is creating a problem. So what I'm going to do is I'm going to divide throughout by y to the power n. So it becomes 1 by y to the power n dy by dx plus p into 1 by y to the power n minus 1 is equal to q. Okay. What we are going to do next is we are going to take this term 1 by y to the power n minus 1 as some other variable, let's say z. Let me differentiate both sides with respect to x. By the way, this is nothing but indirectly saying you are taking y to the power 1 minus n as your z. So let me differentiate both sides with respect to x. So this will become y to the power 1 minus n derivative is going to be, let me just write down the result directly, 1 minus n times y to the power minus n dy by dx is equal to dz by dx. In other words, we can say 1 by y to the power n dy by dx is nothing but 1 by 1 minus n dz by dx. Right? Now this term, as you would see, is already present in our differential equation over here. So I'm going to substitute this term with 1 by 1 minus n dz by dx term. So I can write this term, that is the very first term over here, this term which I am encircling, with 1 by 1 minus n dz by dx. Okay, and this term I can write it as pz is equal to q. You can multiply throughout with 1 minus n, so it becomes 1 minus n pz 1 minus nq. Now remember, n is just a constant, so this doesn't change our game plan here. The game plan was to convert this to a linear differential equation. We have to convert this to a linear differential equation, and we have successfully converted that. So this becomes a function of x. This also is a function of x. So now this will become your new p dash, you can say. This will be your q dash, and you can straight away start with the process of integrating factor and try to solve this problem. Okay, let me take a question which is based on this Bernoulli's differential equation.